This is Euclid Book 10, proposition number 9, and this is the diagram. I only wish the proof was as small as the diagram. I'm sorry to say that it is not. What does this particular proof have to say? The squares on straight lines commensurable in length have to one another the ratio which a square number has to a square number. And squares which have to one another the ratio which a square number has to a square number will also have their sides commensurable in length. Now at this point you're probably scratching your head. Let's go on. But the squares on the straight lines incommensurable in length have not to one another the ratio which a square number has to a square number, and the squares which have not to one another the ratio which a square number has to a square number will not have their sides commensurable in length either. Alright, here's how this works. For let A and B be commensurable in length. At this point we're going to say that B is 2, we're going to say that B is 2 and A is 4. 2 measures 2, 2 measures 4. Okay. I say that the square on A has to the square on B the ratio which a square number has to a square number. So we're going to square 2, and 2 times 2 is 4. We're going to square 4, which 4 times 4 is 16. So now we have a ratio of 16 to 4. That's what we have. For since A is commensurable in length with B, therefore A has to be the ratio which a number has to a number. This is by Euclid Book 10, proposition number 5, in case you forgot. Let it have to it the ratio which C has to D. Now we're going to say that D is 3 and C is 6. So as 2 is to 4, so as 3 is to 6. Okay. Since then, as A is to B, so as C is to D, and you can check that out for yourself, because that's basically 2 over 1, or if you wanted to reverse it around, it could be 1/2 or 2 over 1. Doesn't matter either way you want to look at it. While the ratio of the square on A to the square on B is duplicate of the ratio of A to B, because 16/4 is a duplicate of 4/2. Okay? For similar figures are in duplicate ratio of their corresponding sides. This is by Euclid Book 6, proposition number 20, porism. And the ratio of the square on C to the square on D is duplicate of the ratio of C to D. So we're now going to say that if we square C, it's going to be 36. If we square D, it's going to be 9. And so 36/9 is a duplicate ratio of 6/3. That's what we're going to say. For between two square numbers there is one mean proportional number, and the square number has to the square number the ratio duplicate of that which the side has to the side. This is by Euclid Book 8, proposition number 11, in case you forgot. Therefore also, as the square on A is to the square on B, so as the square on C is to the square on D. Obviously, 16/4 and 36/9 are the same ratio, because when you divide them all out, that becomes 4 over 1, and that also becomes 4 over 1. So the original ratio up here was 2 over 1, now it's 4 over 1. Which means it's a duplicate of the original ratio. 4 over 1, okay, 4 over 1 is a duplicate ratio of 2 over 1. That's how that works. It'd be like saying that 1/4 is a duplicate ratio of 1/2. Same difference. Next, as the square on A is to the square on B, so will the square on B, next, as the square on A is to the square on B, so let the square on C be to the square on D. I say that A is commensurable in length with B. For since, as the square on A is to the square on B, so as the square on C is to the square on D. So in other words, 16/4 equals 36/9. You already know that. While the ratio of the square on B, let me try that again. While the ratio of the square on A to the square on B is duplicate of the ratio of A to B, and the ratio of the square on C to the square on D is duplicate of the ratio of C to D, which we already said that 4 over 1 is a duplicate ratio of 2 over 1. Therefore, also, as A is to B, so as C is to D. Therefore, A has to be the ratio which the number C has to the number D. Therefore, A is commensurable in length with B, and this is by Euclid Book 10, proposition number 6. Next, let A be incommensurable in length with B. Now, let's say that A is 8 and B is 9. Now we're going to say that A is 8 and B is 9. I say that the square on A has not to the square on B the ratio which a square number has to a square number. For if the square on A has to the square on B the ratio which a square number has to a square number, A will be commensurable with B. Okay? In other words, if their squares were commensurable, then the numbers would be commensurable. And obviously these two numbers are not. Okay. Therefore, the square on A has not to the square on B the ratio which a square number has to a square number. So, the square on A has to the square on B. It does not have a ratio that is identical or even similar to the A to B. Okay. Again, let the square on A not have the square on B, the ratio which a square number has to a square number. I say that A is incommensurable in length with B. For if A is commensurable with B, the square on A would have to the square on B the ratio which a square number has to a square number, but it doesn't, therefore A is not commensurable in length with B. Now, they have a poorism. And it is manifest for what has been proved that straight lines commensurable in length are always commensurable in square also, but those commensurable in square are not always commensurable in length also. And then they have this thing called a lemma. And this is kind of supposed to be some kind of a helping step. Don't ask me why, because I don't know. It has been proved in the arithmetical... Okay, I love this vocabulary. It has been proved in the arithmetical books that similar plane numbers have to one another the ratio which a square number has to a square number, and this is by Euclid Book 8, proposition number 26. And that if two numbers have to one another the ratio which a square number has to a square number, they are similar plane numbers. The converse of Euclid Book 8, proposition number 26, and I think that's kind of what they call the opposite of, but don't quote me on that. And it is manifest from these propositions that numbers which are not similar plane numbers, that is, those which have not their sides proportional, have not to one another the ratio which a square number has to a square number, for if they have, they will be similar plane numbers, which is contrary to the hypothesis. Therefore, numbers which are not similar plane numbers have not to one another the ratio which a square number has to a square number. And I'm done with this proof. You've learned a lot tonight in just one proof. I will tell you more in a future video. Stay tuned.